So today's lesson, we're going to take rational and reciprocal functions. Last year we really took a look at rational functions from a very thorough perspective, and we looked at horizontal and vertical asymptotes. Now you may recall the horizontal asymptote had three specific cases in which we compared the degree of the numerator to the degree of the denominator, and it was really quite difficult. So in grade 12 pre-calculus math in Manitoba, what we're going to be doing is we're going to be taking another look at it, but from a transformation point of view. And generally the arguments will be much easier. So recall the definitions from rational functions. So if I just go over here, a horizontal asymptote on a function as x goes to infinity. Now here, as x goes to infinity, that is right-hand side behavior, or as x goes to negative infinity, that would be left-hand side behavior. Now right-hand side, I mean, if this is my Cartesian plane, as the graph gets over here, what's going on, and the left-hand side behavior, if the graph heads over here, what's going on, the value of the function f of x will approach some constant c. Really what we're trying to say is if a horizontal asymptote exists, my function can do all sorts of things, but as x gets closer and closer to infinity, my function will approach my horizontal asymptote. Now recall that my horizontal asymptote is a horizontal line, where its y is equal to, I don't know, 2, 3. Anyways, y is equal to some constant c. On the other hand, on the left-hand side, my function will approach c here. Now, the way that I drew it is that my function approaches the horizontal asymptote from underneath and above from the left-hand and right-hand side, respectively. But really, what is a horizontal asymptote? Just as long as your function gets closer and closer to this constant c without touching it, you're in business. So horizontal asymptote, let's see that. On a function, as x gets towards positive infinity or negative infinity, the value of the function approaches some constant. The y's get closer and closer to some value that is constant c. The horizontal asymptotes illustrate the left-hand and right-hand side behavior of a graph. All right, so what is a vertical asymptote? Now I'm going to maybe draw a vertical asymptote here, so I'll make my axis here. And I really like these formal definitions simply because you have to get used to them. And if you're able to pick apart a formal definition in math, you're going to be in good shape for a university. There's a lot of formal definitions. A vertical asymptote on a function as x approaches some constant c. Now, any constant c, no, it has to be a specific one. So I'm just going to make my vertical asymptote here, right? And you may recall from last year that generally, where do horizontal asymptotes occur? At the restrictions of the function or the non-permissible values. On a function, as x gets towards some constant c, and I'm just going to say this would be x is equal to c. This is it's a vertical line. The value of my function, either, like the y values, go to positive infinity or negative infinity. Which one? I have no idea. Depends on the function. But let's just draw what that might look like when you're able to say, I have a vertical asymptote. So my function, now I'm just going to draw a horizontal asymptote just for fun, right? So for example, my function, as it approaches this vertical asymptote, will go way up. So as x gets closer and closer to this value, y just takes off to infinity. It doesn't need to, it can also take off. So now I'm going to approach c from this direction. So here what we see is that the value of the function goes towards negative infinity. So we say this is as x approaches c from the positive side, as x approaches c from the negative side. We have this thing. So horizontal asymptote is basically as we go all the way off the graph, the function will approach some constant. And a vertical asymptote is as x approaches some constant. As x gets, say, I don't know, this might be 3, right? As x gets closer and closer to 3, the value of the function gets almost to infinity or negative infinity. All right, let's take a look at perhaps why we're dealing with this. A reciprocal function, well, that's kind of ugly how I blocked that, it's bothering me. Much better. A reciprocal function, 1 over f of x, can be obtained by a transformation such that xy, so xy, and this might be on graph y is equal to f of x, gets transformed into y is equal to 1 over f of x. So the point is we take point xy, which is on our parent function, and we transform it into point x, 1 over y. So now this is the reciprocal of y. Now I'm just going to take a look, consider the graphs below. Y is equal to x. Y is equal to x is my line. You may recall there's nothing really too special about this line, but this is my parent function line here. The identity line, this is y is equal to x. And what I notice is that y is equal to x has certain points along the line, which is great. So I'm just going to put points there, there, and there. This is y is equal to x. So, for instance, when x is -3, -2, -1, 0, 1, 2, 3, the y values are, well, the y's are equal to the x, so they're going to be the exact same. So I'm talking about that line that I just highlighted. All right, so now I've mapped points, or points x, y are mapped. I'm going to transform them and create the reciprocal function. And that's how they're mapped. So how do we transform it? We simply take the reciprocal of y. So here's my y value. The reciprocal of -3 is -1/3. The reciprocal of -2 is -half. The reciprocal of -1 is -1. Now that's an interesting one to me. Let's come back to that later. The reciprocal of 0 is 1 over 0. Stop. It is not 0. This is not defined. You cannot divide by 0. This is going to be another important point here. And it's because of the y values, right? The reciprocal of 1 is 1. The reciprocal of a half, or of 2 is a half. The reciprocal of 3 is 1/3. So as I'm graphing this, maybe I'm going to graph this. So now I have point -3, 1/3. -3, -3rd. So that corresponds to that point right there. -2, 1/2. So -2, -half. -1, -1. Wow, that's an interesting point right there. When x is equal to 0, what we see is that the reciprocal function is not defined. There is no point, and even if I have an infinite amount of data, there will still be no point where x is equal to 0. My graph is not defined. Anyways, I'm going to map out these other points here and see what we come up with. All right, just for fun, I'm going to take this point right here. I'm going to take -1/2, comma 1/2, -half, and if I transform that, that becomes -1/2, comma -2. So that goes down there. Now I'm going to take this point right here. I have no idea what that is, so I don't know the x value, but the x value stays the same. I'm going to call this negative 1/10. Wow. When I take the reciprocal, it goes down to negative 10. That's incredible. So same argument can be made on this side right there. I'm going to take that point. This is point 1/2 comma 1/2. If I transform it, it becomes negative 1/2 positive 2. So that goes all the way up here. Same argument I can make for 1/3, 1/3, goes up to 3, 1/4, 1/4, goes up to 4. Anyways, my reciprocal function looks something like this. Now I've graphed this already. So my job is like super easy. It's continuous, so I'm going to put arrows there. And it goes up like this. It's fabulous. Oh, this is looking beautiful. There we are. The red is y is equal to 1 over x. I have graphed the reciprocal function. Now, very simply, or not so simply, I'm going to denote two very important lines. This line right here. Now, if you notice, as my graph went to the left and went to the right, the y values of my graph got closer and closer to this green line. What is the equation of this green line? Y is equal to 0. So my graphs got closer and closer to this green line. In other words, to put it in math speak, as x went to negative infinity, as x got really large negative, or as x got really large but positive, my y values went to 0. So that is a definition of the horizontal asymptote. And when we're denoting a horizontal asymptote, we have to denote it as a line. All right, hope this jogs your memory of what a vertical or a horizontal asymptote is. Now I'm going to take another one, but I'm going to choose hot pink. There we are. Guess what I'm going to talk about now? I'm going to talk about this line right here, which is so incredibly odd because it is a fundamental guiding line of my functions as well. That is a beautiful line, right? Now, it's really interesting, this line, because as x gets close to, let's talk about approaching this line from the negative side. As x gets really close to this, as x gets really close to 0, my y values go down to negative infinity. As my x values get really close to 0 from the positive side, my y values go towards positive infinity. So here, what we have is as x approaches some constant, what is that constant here? It's 0 in this example. We have y approaches infinity, or y approaches negative infinity. So what that means is my y values get either really, really, really large, or positive or negative. And this is called a vertical asymptote. And the vertical asymptote is this pink line. And since it's a line, we have to denote it as such. X is equal to 0. So there we have it. I have graphed the reciprocal of 1 over x. Please practice this graph at home. Please try to understand the definitions of a horizontal and vertical asymptotes. If you took this last year, you may note that if I'm just looking at the value of the reciprocal, the degree of the numerator is 0. The degree of the denominator is 1. Since the degree of the numerator is less than the degree of the denominator, we have a horizontal asymptote of y is equal to 0. Secondly, generally, where does a vertical asymptote come from? It comes from your restrictions. If you remember here, what cannot x be? X cannot be equal to 0. Anyways, a lot of information I just pushed your way. Some of it may be review, some of it may not be review, but please ask in class.